Okay, 1.4, accuracy with measurements. So starting off, we want to look at the word precision. Precision talks about the level of detail, right? That would be how many decimal points does our tape measure measure, right? Does it measure to the nearest, I don't know, 0.1, or does it measure to the nearest 0.001, right? This one would be more precise. Sometimes with tape measures, it's normally a fraction, right? Some tape measures only measure to the nearest 1/4 inch versus some go all the way to the 64th inch, right? The 1/64th would be more precise. When performing calculations with measurements, the calculated value is no more precise than the original measurements, okay? And what that means in our terms is that if we start off with only 2 decimal points, then we can't end with 3, okay? That's what that's going to mean for us. Next up, we have accuracy. That's how close a measured value is to the actual value. So say I take out 5 different tape measures that I've got, and I measure 1 foot and I write it on a piece of paper, right? I measure a foot, or I don't know, maybe it's just 5 inches or something, onto a piece of paper, and I put a little dash at 5 inches from the edge. All those tape measures, they'll be close, but they won't all be 100% the same, right? Because all tape measures are a little bit different accuracy, right? A lot of the time, if you spend more on a tape measure, you'll get a slightly more accurate tape measure or a slightly more accurate measurement. Another way to think about this would be, how about I buy a whiteboard from a company and they list it as 36 inches, and they know 100% certain that it is 36 inches wide, right? And then I take my tape measure and I measured it, and well, my tape measure says that it's 36 and a 16th inch, or a 16th inch, right? I know 100% that the real value, the actual value, is 36 inches. But whenever I measured it with my tape measure, the measured value is 36 and a 16th. So my tape measure is not 100% accurate, right? So that's how we think about that. Accurate is how correct is it. Precision is how detailed is it. So number 1 here. A hotel had a total of, I'm not even going to read that number, that many guests and staff staying at the hotel in June. The water bill for the month shows a water usage of that many gallons. Estimate the water usage per person. Now we're talking about precision and accuracy, so let's think about these numbers real quick. The number of guests, or the number of people, I guess that would be. That's probably correct, right? There's not a half person, right? There's not a quarter person. So we're going to say there's exactly 6,974 people. Now we look at the water usage. It tells us this many gallons. Well, odds are the counter that they have outside has to be rounding to the nearest gallon. Because how often do you think a water bill or a house or a hotel or whatever it is actually uses an exact gallon, right? It's normally going to be a decimal, right? So there must have been the meter that was measuring this had to be rounding to the nearest gallon, okay, the nearest whole gallon. So that's going to be useful towards the end of this. So to figure out the water usage per person, we're going to take our people. So what is that? 6,974. And we're going to divide 6,82057. We're going to divide gallons divided by people. And whenever I type that in, let me type that in the calculator. 6,82057 divided by 6,974, I get 97.79 repeating. And this is gallons. Now, we started off with a whole number of gallons, so we're going to need to end with a whole number of gallons. So whenever we round this, we'd have 98 gallons. Okay, moving on to number 2. You use a tape measure to measure the dimensions of a regular canvas, right? Canvas like the thing that we would paint. Its dimensions are 50.8 and 40.6. Estimate the area, and that should be area, of the canvas. Well, we know that area is base times height. So I'm going to multiply those two numbers together. So 50.8 times 40.6. That gives me 2062.48. And this would be measured in inches squared. Now, we need to think about this. We started off at the nearest 10th inch. We're going to need to end with the nearest 10th inch. So I'm going to round this to 2062.5 inches. Oh, and inches squared. There it is. All right, so you got to make sure that we round. So that is how we do that. And let us move on to number 3. So an investor purchases a field in hopes of turning it into a solar farm, right? You've seen pictures of solar farms probably. A bunch of solar panels in a field. The field is that many square meters. The solar panels they intend to purchase are 65 wide and 39 inches long. How many solar panels can fit in the field? So whenever we start thinking about rounding, we can look here, 0.9. That's the most precise number that we have. So we're going to need to, at the end, whenever we're all done, we're going to need to round to the nearest 10th, the nearest 1 decimal point. Now you'll see here that I've already written that 1 inch is 2.54 centimeters and a meter is 100 centimeters. And we're going to need to use those to turn these inches into meters. Right? We started off with inches here. We're going to need to use meters. So I'm going to take 65 inches. And first I'm going to use this top conversion factor. I'm going to say, well, 2.54 centimeters is 1 inch. Right, and I can say that the same thing about the 39-inch one. All right, what this does is it cancels our inches and inches, and now our units would be centimeters, but I really need meters. So I'm going to use my other conversion factor. I will, what is that? I'll use the meters on top, 1 meter on top, 100 centimeters on bottom. And now whenever I cancel on top and bottom my centimeters, I'll be left with meters. So let's type these into the calculator. I'm going to first type in 65 times 2.54 divided by 100. I get 1.651. And on the bottom, whenever I type that in, I will get 0.9906, right? These are both in meters. Now, it can be tempting right now to round, but what we want to do is we want to wait to round, and we want to do that later. Okay, we want to do that at the end of the problem. So now that we have the dimensions of our solar panel, right? These are the dimensions of our solar panel, the one that we're going to buy from the factory. We need to figure out how large is the solar panel? How much area does it take? So solar panel area. And we're going to find the solar panel area by multiplying those two numbers. So I'm going to say 1.651 times 0.9906. And that is going to give me 1.6355. And I did round there just a little bit. And that's going to be meters squared. All right? That's one solar panel. Now we need to decide how many solar panels total can we fit. So I look here, that's how large my field is. So I'm going to take my field, 32374.9, divided by our solar panel measurement, 1.6355, and I get 32374.9 divided by 1.6355, and I get 1979.5.11. Now, one of the things to notice here is that we've got this 0.11. For starters, we can't have 2 decimal points, and also, does it make sense to have a fractional solar panel, right? We're going to assume that they're not going to have this company custom make solar panels that are like fractional size, so we're just going to round down to the nearest whole solar panel. So we'll round down to 19795 solar panels. And hopefully that's spelled right. All right. Number 4, continuing from number 3, one solar panel can produce that many watt-hours of electricity per day. Now, whenever we see watt-hours, watts are always measured in hours. So we can just kind of ignore that word hours. It's just going to confuse us. How many kilowatt hours, again, I'm going to ignore that hours, can the field produce in 1 hour, right? So a solar panel produces 1060 watts per day, watt hours per day. How many can it produce in an hour? So I'm going to take this 1060 and divide by 24 to give us per hour. So 1060 divided by 24, that gives me 444.16 repeating, right? So this is watts per hour. Now, we could also convert these watts into kilowatts. And one of the ways that we can convert watts to kilowatts, this is a metric conversion really easily, is to move the decimal spot 3 spots. So this turns it into 0.04416. Well, let's turn this into a 17. There we are. And this is kilowatts per HOUR per hour. Now, this here, just to remind us what we're doing, that's how many kilowatts a solar panel produces in 1 hour. So we need to multiply by the number of solar panels that we have. So 0.04417 times 19795, that gives me 19795 times 0.04417, that gives me 874.345 kilowatts. And now we need to look back at rounding. And since we're continuing from number 3, let's look all the way back up at number 3. Number 3, we rounded to the nearest 0.9. Does that really make sense? Yeah, we've already rounded based off of that one. We rounded in this, didn't we? In their solar panel count. These watt hours are to the nearest whole watt. Let's go ahead and round to the nearest whole kilowatt. And there we are. This is a 874 kilowatts per hour, right? And I believe there is a problem similar to this on the homework. I think it might even use some of these same numbers, so make sure that you have that. Now, just to remind us, we're talking about precision and accuracy. A lot of the time, precision and accuracy is kind of muddled in with the term estimate or round, you know. And a lot of the times I use those words, but they're a little bit different. But for most of the math that we're going to do on tests and stuff like that, I'm either going to tell you very explicitly what to round to, or it's going to be a very obvious problem, like maybe number 1, like how you know that you're supposed to round to the nearest gallon. Okay, so don't think I'm going to try to trick you. I'm not going to do that. Look at the homework and email me if you have any questions. All right, that's all.